All right, welcome back. Happy Wednesday. Today is March the 16th. We are going to cover working with radicals. It's going to seem like a brief departure from our previous 2 days on exponents, but next class we're going to tie together the radicals we're talking about today with the exponents we've talked about previously. Speaking of our next class, it is not until March the 28th. Spring break starts this coming Friday, so we have Friday off, and then we have all of next week off, and then we return on Monday, March 28th. Okay? All right. So speaking of spring break, there are a couple of resources available to you that I want to make sure you know about in case you feel like you are behind and want to catch up, or better yet, if you feel like you're on the ball and want to get ahead. Oftentimes, it's kind of a sprint to the finish once we come back from spring break during this semester. And if you put yourself in a good position coming out of spring break, might make all the difference in terms of making the rest of the semester more manageable for you. So 2 resources available to you. Number 1, my YouTube videos are available 24 hours a day. And so if there's topics that you feel like you need a review on, you can go check them out. You can go look at the videos for the practice problems packet. If you're really feeling inspired to like get ahead in the game, all right, so the videos don't exist yet for the stuff we haven't done, but they exist last semester, and it's not too hard to go to my channel and find the whole playlist from last semester. And the packet for last semester doesn't look a whole lot different from it does right now, so you could get ahead. Another resource available to you is peer tutoring. Peer tutoring is here next week, Monday through Friday. Not this coming Friday and not this coming Saturday, but they're available all of next week. And I expect that peer tutoring is very underutilized over spring break. So you could get lots of peer tutoring appointments, not just for math, although clearly that's the best subject, but like any other subject, you could maybe come in and get some work done. All right. So we're starting today on 127, a little bit unusual in that we're going to do a demo and then an activity. That's typical, but then we're going to come back and do a second demo and a second activity. So that's the unusual part. Okay, today we are going to simplify expressions that contain radicals. Here we go. Number 1, we know that the square root of 49 is 7, and the reason it's 7 is because 7 times 7 is 49. Easy. Similarly, the cube root of 64 is 4. That little 3 in the front of the radical there is saying, find me a number that when you do 3 copies of that number all multiplied together, you get 64. And that magic number is 4, because 4 times 4 times 4, 3 of them is 64. All right? Okay, so some vocabulary. Whenever you see this kind of a symbol here, the thing inside is called the radicand. The little number in the front is the index. And then the radical sign is that funny looking symbol there, okay? Just some vocabulary. All right, let's take a look at number 3. I'm just going to introduce a nice property of radicals for us. The square root of 9 times 4. Forget properties. This is really saying the square root of what single number? 36, right? Just do 9 times 4. What is the square root of 36? It's 6. The answer there is 6, no question. Separate problem. Square root of 9 times the square root of 4. This is saying do the square roots first. How much is the square root of 9? 3. Then I'm copying the dot. Square root of 4 is 2, and 3 times 2 is 6. And it is no coincidence that these are the same. In fact, they will always be the same. Multiplication inside of a radical works really nicely. Here's what it says. If you have 2 guys multiplied inside of a radical, you can separate them and do 2 radicals and multiply at the end. In the first example, we multiplied first and took the square root second. In the second example, we did the square roots first and multiplied second, and it always works out to be exactly the same answer. That is written up here. Turns out it's not just true for square roots, but for any roots. So that little n is saying, hey, it could have been a cube root or fourth root, any root. Multiplication, really nice. Same kind of thing is true for division. If you have a division inside a radical, you could split it up into 2 radicals and divide at the end. Go in the other direction, if you have 2 radicals divided, you could put it together and make 1 radical. Works both ways. So let's try number 5 here. One of our few calculator active problems today. It says find the value of each of the following. You won't need a calculator, I'll just do it up here. Square root of 9 plus 4. Okay, no shortcuts. This is really saying the square root of 13. Okay, so the square root of 13, I don't happen to know off the top of my head. So we can type it in square root of 13. Like somebody just, yeah, 3.6 and change, okay? So this is around, away 3.6. Let's do that same problem, but in the other order. Square roots first, adding second. What's the square root of 9? 3. Copying the plus sign. What's the square root of 4? 2. It is 5. Are they the same? No. So no matter how tempting it might be to see the square root of 9 plus 4 and say, oh, I can just do the square root of 9 plus the square root of 4, you can't. It just doesn't work. Up above, we got 6 and 6. But here we got 3.6 and 5. It's not the same. So really, really tempting to think that you can do something with the square root of x plus y. In your head, you might be thinking, square root of x, I'll write it, and then we're going to get rid of it. You might be thinking, oh, I can just do the square roots separately. But we just proved that you can't. You didn't get the same answer by doing them separately, okay? So tempting, but wrong. If you see addition inside of a square root, big red flag says don't do anything. Same red flag for subtraction. You cannot do anything with the square root of subtraction or addition. In the box up here in this table, multiplication, yeah, you can do something. Division, you can do something, but not addition, not subtraction. In particular, you're going to see stuff like this pretty often, square root of a squared plus b squared, and you might be tempted to think, oh, I can just do the square roots separately. What's the square root of a squared? A, right? And the square root of b squared is b, and so it might be tempting to see that expression and say, oh, it's just a plus b. It isn't. Just can't do it. Okay, let's take a look at number 7. 7 talks about the fourth root of 48. Fourth root of 48. Now, we looked at the cube root of 64 earlier, and some couple people just said 4. Fourth root of 48, maybe that's just a nice number that we should know. Now, you're not going to be using a calculator on the upcoming quest or on any of the activities today, but we are going to use that first page reference sheet, the perfect powers table. So just flip over there real quick. I'm looking for the fourth root of 48. It's the very first page of this packet. And so if I'm looking for the fourth root of 48, I'm looking in the column that says fourth powers. Yep, perfect fourth powers. And do you see the number 48 in there? No, we don't. So it seems like we can't do anything with that. And if I typed in the fourth root of 48 on the calculator, I would get some decimal. Okay, but it turns out we can simplify the fourth root of 48. Here's how we're going to do it. First of all, we know that multiplication inside of a radical is something we can work with. So the natural idea is to take that number 48 and change it into two things multiplied together. Okay, we have tools for multiplication in a radical. So for example, 48 is 24 times 2, yeah? And once it's multiplication, my property up there in that table says, hey, I can split this into two radicals multiplied together, right? Fourth root of 24 times the fourth root of 2. Yes? All of those equal signs are valid. Is the fourth root of 24 anything nice? If you're not sure, look at your table again. It's not. Is the fourth root of 2 anything nice? It's not. We haven't told any lies up here, but we haven't made any progress because I can't go any farther. So instead of factoring 48 into 24 times 2, I want to think of factoring 48 in a different way. So I'm going to show you the good way, and then I'll show you how I came up with this good way. So 48 is for sure 16 times 3. Once it's multiplication inside a radical, I can split it into two radicals multiplied together. And the fourth root of 16, you can read off of the chart if you don't happen to know it. What is it? It's 2. And so then we change the fourth root of 16 to a 2. Is the fourth root of 3 anything nice? It's not. So we're just going to leave that in the final answer. So there's our answer. And we say that this thing right here is simplified. It's equal to the fourth root of 48, but it is a simplified version. If I were to type fourth root of 48 on the calculator, I'll get some decimal. If I type in 2 times the fourth root of 3 on the calculator, I'll get exactly the same decimal. They're just two different ways to talk about the same number. You guys have a lot of experience simplifying things. For example, 3/6 is the same as 1/2, right? You know how to simplify fractions. This is what it means to simplify a radical. It means you factor out the biggest possible thing that you can. All right, so what made factoring 48 into 16 times 3 work, whereas factoring 48 into 24 times 2, which is legitimate, didn't work? Jeff? Yeah, perfect fourth power. Yep. So what number was a nice number that we built? Is that 16, right? 16 was in our perfect fourth powers list. So if you are looking at the number 48 and trying to decide, well, how should I factor it? Because 48 has a lot of factors. You just go to your perfect fourth powers list. You say, okay, does 2 go into the, sorry, not 2. The first perfect fourth power on our list is 16. So we just start there and we say, does 16 go into 48? And the answer is, yeah, it goes in 3 times. If it didn't go into 48, I'd look at the next number. What's the next number on my perfect fourth powers list? 81. And I would say, does 81 go into 48? No, it's too big, right? And if I've gotten to 81, then I'm done. I can't go any farther, and it wouldn't be able to be simplified. But it's not just factor 48 in any willy-nilly way you can find. It's a very concentrated, check this very small list of numbers. It takes a lot longer to look at 48 and say, okay, can I divide by 2? Can I divide by 3? Can I divide by 4? Can I divide by 5? The answer to several of those questions is yes, but none of them is helpful. The first one that's helpful is, can I divide by 16? Okay, so don't start and divide by 2, 3, 4 every time. Divide by the things in the list. Okay, let's take a look at this guy here, number 8. We're going to simplify square root of 12 minus 2 times the square root of 75. The answer is written up above. I'm just going to write it down below. Square root of 12 minus 2 square root of 75. Maybe go ahead and copy along as we do this together. I'll hide the answer, which is on the page. Okay, square root of 12. It's not a nice number. It's not a perfect square. You look at your perfect squares list. What's the first number on our perfect squares list? It's 4, right? We ignore 1. 1 doesn't help us. So we look at 4. Does 4 go into 12? It does. Fantastic. We found our winner. We're going to take 12 and write it as 4 times something. And you just got to figure out what the something is. What is the something? 3. We're going to be doing a lot of rewriting here as we talk about radicals and exponents. And every time you rewrite, it should be obvious to you that it's equal to the thing from before. 4 times 3 is just another way to say 12. Copying down, minus 2, copying the square root symbol. 75, is it a perfect square? 75 a perfect square? It's not. So we go to our list of perfect squares. We look at the first one, it's still 4. Does 4 go into 75? For sure it doesn't. 75 is not an even number. The next number in our perfect squares list is, it's on the very first page, yeah. What's the next one after 4? Is 9. Does 9 go into 75? It doesn't. Next one is 16. Does 16 go into 75? Again, it's even. 16 is even, 75 is odd. The answer is no. Next one after 16, 25. Does 25 go into 75? Yes, we found it. You still have to have 75. 25 times what? 3. Good. And I'll say again, it's not just any factors of 75, it's specific ones, a very small list. It's true that 5 goes into 75, goes in 15 times, but who cares? 5 is not helpful, 15 is not helpful. So you focus your attention on that small list of helpful numbers. They are the perfect squares. Okay, next thing we're going to do. If you see a square root on a product, you are welcome to split that up into 2 square roots with a multiply in between. That was the property we saw up above. So 4 times 3 is not simplified. We're going to get to something that we call simplified. Over here, same idea, copying the 2, splitting this square root up into 2 different ones with a multiply in between. Okay, and the whole point of those factorings was this step right here, the square root of 4 is nice. What is it? It's 2. So 2 times square root of 3 is what happens with the first radical. Minus, okay, now this is something, it's a moment where some people get confused. I'm copying that 2. The square root of 25 is 5. And I'm copying the square root of 3. And that space in between the 2 and the 5, some people get confused as to what operation is in there. It's multiplication. Some people introduce a plus sign. Bad, bad, bad. There's no plus sign, right? There is an invisible symbol right here. What is it? Yeah, that symbol's okay, meaning multiply, right? So it's implied. It was an implied multiplication from before. It's been implied the whole time. We finally get in trouble here when a 5 pops out of the problem, but it's still multiply. So we got to be clear. We knew it was multiply from the beginning. Okay, almost done. 2 square root of 3 is copied, minus the 2 times the 5 now get smushed together and make a 10 square root of 3. Okay, and this one is not quite done. It's correct, but it's not simplified as far as it will go. 2 square root of 3 minus 10 square root of 3. Guesses on what that simplifies to? Negative 8 square root of 3. Negative 8 square root of 3. They don't. They don't. Here's why. Suppose that that I think of this guy as being 2x. So I'm just thinking of that square root of 3 as being x. What is this other expression? Is minus 10x. Same x, right? And 2x minus 10x, we all know, is negative 8x. You don't mess around with the x. You just copied it, right? Doesn't become x squared. Doesn't become 2x. It's just x. So it's the same idea. So that's our answer, negative 8 square root of 3. And that one's simplified. And again, if I were to type this into the calculator, I'll get some decimal. And if I type the original problem in, I'll get the same decimal. But I'd much rather mess around with the last guy than the first guy. Questions on that? Yes. Yes. Yeah, if those two square roots didn't end up both being exactly the same, square root of 3 in this case, we couldn't do anything at the end. Like if it was 2 square root of 3 minus 10 square root of 5, that's it. We don't go any farther. It's only because they were matching up. Jeff, can you read nice and loud number 9 on the next page? Yes, please. Okay, so that's what Jeff had predicted earlier and Evan kind of confirmed. It's got to match up exactly in order for us to smush them together. Okay, last example here, number 10. Radicals that are not square roots. The cube root of 64, we saw that one earlier today. I'm looking for a number that I can multiply 3 copies of itself and get 64. Some of you just have this number memorized, but if you don't, you look at the chart. I'm not going to have the calculator with you. So you look at your chart. Which column are we looking at? The cubes, the perfect cubes, and we're looking for the number 64. And then you go all the way to the left, and what number do we find? 4 is correct. And then the 4th root of 16, make sure you look in the right column, because 16 appears in a couple of different places in this table. So we're looking in the perfect 4th powers, and we find 16 in the row 2. Questions on that? All right, so like I mentioned, there are 2 activities today. So you're going to do this first one until I call you all back together, and we'll look at another demo. But let's see how far we can get. Again, no calculators here, but do use that table. Okay, so folks, we're doing some very good work with the first activity. First activity involves only numbers. It was all numbers you were playing with, no x's, no y's, no variables, right? The same idea that we had with the numbers is going to apply to the variables, but of course dealing with variables is a lot harder than dealing with numbers. So that's what this second demo is about. But just be prepared, it's going to be tougher. Okay, we already know, we've seen today in fact, that the cube root of 64 is 4. I'm going to write that fact in another way. I'm going to write 64 as 4 cubed. I'll buy that that's what 64 is. It's 4 times 4 times 4. And so this equation just becomes that equation, another way to say the same thing. And written in that other way, I can think about this cube root symbol and this cubed symbol as canceling. They're opposites of each other. Cube rooting something and cubing something undo each other. And so we just cancel those 2 things circled in red, and what do we get as the answer? It's 4. So if somehow you can get a radical into this like highly desirable form where you can see the index, remember that's the little 3 in the front of the radical, is exactly the same as the power, then they cancel. And you just get whatever's inside. In this case, it's 4. Okay, so if we wanted to, for example, look at the cube root of x cubed and say, hey, the cube root and cubing are opposites and they cancel. And what's the answer here? Is x. So the cube root of x cubed is just x, in the same way as the cube root of 4 cubed was just 4. Okay, so then what about the 4th root of x to the 4th? It's the same thing. So what's the answer? X. Fantastic. So if you can get the index to match perfectly with the power, they all disappear. They all cancel with each other, and you're just left with whatever's inside. Let's take a look at this 5th root of 32x to the 45th. I'm going to do this one up above, even though it's written out down below. Try to ignore it. Okay, I would really like to get the things inside my radical to be 5th powers, because that index of 5 would cancel with those 5th powers. 32 is really, whoops, 32 is really what number to the 5th? If you're not sure, look at your chart. 32 is what number to the 5th? 2. I currently have x to the 45. I'd really like that to be something to the 5th power. I'm going to put an x here. I'm going to put a little box here. I'm going to fill a number in the box in a second. But what's the property for the box and the 5? You multiply those exponents. That's a familiar property from 2 classes ago, right? So I'm trying to put a magic number in the box so that when I multiply it by the 5 that I'm trying to build, I get the same 45 that I had before. What's the magic number? It's 9. Everybody agree? So we should see that this new expression I've written is still exactly the same as the original. It's still 32x to the 45th, right? We see x to the 45 by multiplying, and 2 to the 5th is just another way to say 32. And then once I've got a 5th root and 5th powers, everything blows up, and what am I left with is just the stuff in the parentheses. So what's the answer here? Is 2x to the 9. You see it? It's detective work. Yeah. You got to recognize the stuff inside that radical as being some other stuff raised to the 5th power. And we got to do work to figure out what that other stuff is. But once we've done that work, problem's easy. Everything just disappears. Okay, so let's take a look at number 5 down here. 4th root of x to the 20. Let's try this one together. 4th root. What power would I love to see on these parentheses here? I'd love to see a 4 there, right? Because it's a 4th root, I want to build a 4th power. I'm going to put an x. I'm going to put a green box. I'm going to say, hey, I had x to the 20th before. Whatever you put in that box, it better still give me x to the 20th. What's going in the box? It's a 5, right? Because we know those powers multiply. So this equals x to the 5th. Done. The 4th power and the 4th root cancel, and you just get what was in the parentheses. All right. Now, some of you might be predicting a shortcut here, because there is some magical thing you can do with the 20 and the 4 to build the final answer of 5. What's the shortcut? It's divide. Let's not use the shortcut today or on tonight's homework. Maybe next class we'll start using the shortcut, but I'd really love for that shortcut to become intuitive with lots of practice of rewriting things, being algebra detectives, like Jeff said. Let's take a look at part B. Equals cube root. I'd really love 3rd powers here. We're going to deal with the 64 and the x to the 27 separately. 64 is really what number to the 3rd? It's really 4 to the 3rd. 4 to the 3rd is just another way to say 64. X to the 27. What magic power are we putting up here? So I still have 27 as a 9. Bye-bye. Don't use the division shortcut. Just be a detective. Take your time on these. And then lots of things blow up. And what's our final answer here? 4x to the 9 is good. Okay, let's take a look at number 6 here. All right, 6 is the toughest problem of the day, but it's something that you're going to see on the homework, and it's something you're going to see on the quest. So we've got to be able to handle it. Cube root of 16x to the 4 times the cube root of 2x to the 19. So the fact is, all of the steps are written out here on the side. Can we find some space nearby, and we're going to ignore the fact that this problem is all the way done already? Maybe on 133. Can we jump to page 133? And we're just going to copy this problem on 133. All right, can somebody read that problem to us? It was a cube root of what? What's the beginning, Liam? 16x to the 4, and then times cube root 2x to the 19. Okay, so everybody copy that on 133. And we'll do this one start to finish. And again, it's going to be tough. Now, the fact is, we could clean up the first radical, simplify it. We could clean up the second radical, and then we could multiply them together, but we're still going to have a radical at the end, which we might still need to clean up at the end. So I'd much rather smush these things together and make one radical first. And I'm allowed to do that because I know multiplication is good inside of radicals. So we buy that I can just make one radical with these two guys multiplied together. That was that nice property we saw for radicals. That's fair. The nice thing is we've taken two radicals and made one, right? So whatever we're going to do, we're only going to have to do once here, not twice. And actually, I think we would have had to do a third thing if we had left it in its original form. Okay, let's figure out what this guy really is by smushing together the stuff that goes together. Is this a FOIL problem? I haven't used that word yet this semester, but is this a distributing? Like, do I do 16 times 2 and 16 times x to the 9 or 19? No. The distributing is when you have addition, like two parentheses with addition inside. That is not this. This is just multiply and shuffle things around in your mind. 16 times 2 is 32. X to the 4 times x to the 19. What do we do with those powers? Add. So that is really just 32x to the 23. Add the powers, right? That's our old property. Now, what we're about to do is tough, but at the very least, we have gone as far as we can inside that radical and made it as simple as possible. It's in our best interest to make that simple before we do this complicated thing. So here we go, equals cube root. Let's take a look at that 32. Is the cube root of 32 anything nice? It's not. But we simplified radicals with numbers in them in this activity today. So we're looking for a nice number that goes into 32. What column should we be looking at in our table? Perfect cubes. Looking for a perfect cube that goes into 32. The first perfect cube on your list is 8. Does 8 go into 32? Yes, that's the winner. So 32 is really 8 times something. 8 times what? 4, and that's the leftover stuff, which is okay. So we had 32, we still have 32, just written in a better form. Okay, let's take a look at this x to the 23rd. I'm gonna do a little calculation here on the side. Cube root of x to the 23rd. You don't need to write this. If I'm being a detective, what power would I really like to put up here? 3. I want it to match that index. And we'll put our favorite green box right there. Again, what happens to the box and the 3? Multiply those together, right? Is there a nice number I can put in the box to make 23 when I multiply? The answer is no. It'd have to be a fraction. Fraction powers exist. We're going to tackle them next class, so not today. So there's nothing, no integer I can put into that box, right? Okay, so how about this? I'm going to play a little game. Suppose that I didn't have 23, but rather I had 22. Just going to peel one of them off. I didn't like having 23 in there. Let's take away one. Can I do anything there? No. So that was so much fun. Let's try it again. I'm going to peel one more. Peel one more. X to the 21. Can I handle that? I can. So by peeling off enough x's, eventually I get to something I can handle, right? What makes 21 good with respect to that 3? 21 has a factor of 3, right? So 21 is a multiple of 3. There's a 7 involved, right? You don't need to memorize it as a shortcut, but that's what makes 21 good, where 22 and 23 were not useful to us. So let's come back up here. We've decided that x to the 21 is a really great thing inside of a cube root. But I can't just ignore the fact that I had 23 x's there. So I still need to put something here that makes me still have 23 x's. X to what power? To the second, right? I'd ignored two, I peeled off 2 of those x's. I can't just get rid of them. They're still there. You all agree I still have 23 x's? Great. Now, I'm going to break this guy down again. I told you this would be tough, right? I'm going to break this down again into 2 radicals. One of the radicals is going to be all the good stuff, all the nice stuff that we built. The other radical is going to be the leftovers. Of the 8 and the 4, which one is nice inside of a cube root? 8. 8 is there in the good radical. 4 is leftover. X to the 21 and x squared. Which one is useful with regards to that index of 3? It's the 21. You built the 21 over here in red because something good was going to happen. So x to the 21 goes in the good radical. X squared goes in the leftover pile. Okay, I promise we are almost done. We made that good radical, the 8 and the x to the 21, because we could write everything as perfect cubes, which is useful to us. So this guy right here is what we're rewriting right now. 8 is really what number cubed? 2 cubed. X to the 21 is really x to what number cubed? Is the 7. It's the 7 that Joel shared with us, right? It's the green box, 7. And then over here, we're going to put the other radical, and there isn't anything to do with the other radical. It's just leftovers, and it's going to be in the final answer in its current form. Last step, making all of the stuff explode. So what do we get from this first radical? 2x to the 7. Everybody see it? Cube root, and all of those cubes that we worked so hard to build cancel. And then I'm copying the leftovers. I told you, it's not easy. There are shortcuts floating around. Do not use any of them today. Go in super slow motion. Make sure that every time you rewrite something, you rewrite it in a form that it's still clearly equal to the thing you had before. We had x to the 23, right? How did we rewrite that x to the 23? Right, x to the 23 became x to the 21st and x to the 2nd. Some people want to use this shortcut. They say, oh, 21 divided by 3 is 7, and yes, x to the 7 ends up in your final answer. But if you try to use the shortcut before you've developed intuition, you might end up thinking that x to the 7 should be inside of the radical as opposed to outside of the radical. You might think that that x squared, the leftover 2 x's that we had to pull off, ends up outside instead of inside because it's all murky for you. It's okay for it to be murky, but while it's murky, go slow. Don't go fast, right? So every time I want you to go slow. Make sure that you rewrite things so that they're clearly equal to what they were before, but hopefully in a little bit better form. I will walk around. The second activity starts on the next page. Or actually, well, I guess we have to go back a couple of pages. So 131. No calculators and no shortcuts.